The original rack of memory. Several times now we have mentioned the existence of words in the controller's memory that are permanently associated with an I/O module. To better understand how the I/O structure arrived at its current designs, let's take a look at one of the earliest approaches. Ponder the title of this slide just for a moment. A rack of memory. And there's a full rack of memory, a half rack of memory, and even a quarter rack of memory. Today the terms rack and chassis are used interchangeably, but this was not always the case. Let's take a quick look at this, and if you still have some of this older I/O structure to work with, this will serve as a really good review of this hardware and its relationship with the memory structure in a PLC. The original 16-slot chassis was referred to as a rack of memory. Let's see why. The I/O modules back then were 8-point modules, not 16. Even though the memory was 16-bit words, the electronics was large enough that cramming 16 input circuitries into one card was difficult, so they built 8-point cards. Remember from our earlier discussions, the processor takes a snapshot of the on and off state of each input across the backplane and then stores this input image in a word in memory at a location identified specifically for that physical location in the chassis. So if you have something marked 0 in the chassis, it's going to be 0 memory. 1 in the chassis, 1 in memory. Now with 8-point modules, 2 of them would be required to make up one single word memory, because remember, memory is 16 bits, bits 0 through 15. The first indication of this is the identification at the top of each group of 2 slots. So if you look at the illustration, you see something marked module group, and you see a number above the center of 2 slots. So the first 2 slots make up module group 0. The second 2 slots, module group 1. I think you're starting to see this. If you got 8 points in each slot, it's going to take 2 slots for word 0, 2 slots for word 1, etc. These are referred to as module groups, module group 0, module group 1, and so on. Remember also that I mentioned when we were examining various base number systems that octal or base 8 was used originally for I/O addressing, I/O locations. Well, here it is. Notice that the top of the 16-slot chassis is organized into 8 module groups 0 through 7, and each group has 2 slots representing a 16-bit word memory. A module added to the chassis and placed in slot 0 of module group 0 will be associated with the lower byte in word 0 in memory. Slot 0, module group 0, word 0, lower byte. If it is an input module, the state of these 8 inputs will be recorded or stored in the first 8 bits in the memory location 0 associated with module group 0. Adding another module in the upper slot, slot 1 of module group 0, will be associated with the upper byte of word 0 in memory. Because of the association of these 2 modules with the upper and lower byte in memory, they are sometimes referred to as the lower and upper slots of the module group, or the low and high slots. Nonetheless, you get the idea. One module group is always associated with one word in the PLC's memory. This was a simplification of the relationship between the I/O chassis and memory. Now, we will look at the actual configuration of I/O memory, because I kind of oversimplified this just to get this started. In the first PLCs, the memory was physically very large and extremely expensive. For that reason, most of it, if not all of the memory, was permanently mapped out for I/O. Timers, counters, program files, etc. This processor has memory allocated for one rack of I/O, or 8 module groups. To allow the user to install input or output modules in whatever combination they needed, and in any location within the 16 slots, it was necessary to set aside 8 words or 8 module groups for inputs and an equal complement of 8 words or 8 module groups for outputs. But keep in mind, we've only got one chassis with 16 slots or 8 module groups. But because we don't know whether we're going to put input or output modules in what slot, we need to set aside memory in case you decided to have 16 8 input cards or 16 8 output cards or any combination thereof. So I think you can see that if you mixed and matched input and output cards in this 16 slots, no matter how you did it, only half of that memory would be used. Because remember, you have to have memory set aside in file 0 in case you put an output card in that slot. You also have to have memory set aside in file 1 in case you decide to put an input card in that slot. Let's slide some modules into this chassis to demonstrate this. First, we'll plug an output module into the lower slot of module group 0. For programming purposes, these 8 bits of memory will be addressed from the logic to control the 8 outputs connected to the screw terminals on this 8-point module. The lower slot is associated with a lower byte in memory. Notice that the lower slot in module group 0 went into the lower byte of word 0, but word 0 in data file 0, which is for outputs. Adding an input module into the upper byte of module group 0 does not associate with the upper byte adjacent to the lower byte in word 0 of file 0 that we were just looking at, but instead it is associated with the upper byte of word 0 in file 1. Input modules have their images stored in file 1. Output modules have their images stored in file 0. This means that no matter the combination of input and output modules, only half of the memory will be used. There is more to this story, but this is sufficient for the scope of this presentation. One last point. When 2 slots are associated with 1 word in memory, it is referred to as 2-slot addressing. As time progressed, and electronics became smaller, 16-point modules became available, and they were manufactured to fit in the exact same slot as the 8-point modules. With 16-point modules, each slot was now associated with 2 words in memory. Therefore, each slot was a module group, and 16 slots became 2 racks of memory in one chassis. With these older processors, if you wanted to take advantage of the 16-point modules in a 16-slot chassis, you could not simply expand the memory allocation. You had to purchase a new processor that had 2 racks of memory permanently allocated for inputs and outputs. Notice in this diagram that there are 16 slots marked in 2 groups of 8 module groups, and each module group is a slot. Memory is organized with 16 words, file 1 for inputs, and a complement of 16 words, file 0 for outputs. Rack 0 is associated in the memory layout of the PLC in both the output file, file 0, and in the input file, file 1, which means that there are 2 words in memory associated with each physical slot in the chassis. Let's populate several slots to demonstrate how this works. First, we will slide an input module into the first slot, slot 0 or module group 0 of rack 0. There are 2 words in memory associated with the slot, one in the output file 0 and another in the input file 1. This being an input module, the image of the states of these 16 inputs will be stored in word 0 of file 1, the input file. Now slide in an output module into module group 1, associated with 2 words in memory as well, but it will be stored in word 1, the second word in output file 0, as you can see. In summary, this little side trip into an older I/O memory structure was presented primarily to firmly plant into our minds that PLCs collect and distribute I/O data 1 slot at a time over a common backplane, and that the I/O data is stored in memory for use by the program. The program never directly accesses the I/O modules for the status of an input, nor does it ever send the result of a rung of logic directly to an output of an output module. The logic works entirely with information stored in the PLC's memory and controls information stored in the PLC's memory. The program does not directly control the outputs. The program controls the output file, which is then later transferred to the output modules. This is where a PLC separates its behavior from a relay circuit. In a relay circuit, the instant that an input type device changes state, the effect is immediate, and when continuity is available, the load is energized.